Hello, everybody. Welcome back to Chapter 12 lectures. Today we're going to go ahead and finish 12.3 and then probably some more of Chapter 12 here. So last time in 12.3 we were talking, this section is called the regression equation. So we developed the equation for finding the regression line. And I say we developed, we really just said what it is because as we noted, we really need calculus in order to fully derive the regression line. But this is the line right here. So it's going to be y hat equals a plus bx, where a is this and b is this. So it's a little messy, but these are all things we're able to calculate, right? We're able to calculate y bar. That's just the average of the y values. We're able to calculate x bar. That's the average of the x values. And then this is just, b is just some combinations of all of that. Remember, this symbol here means add them all together. But we were using the alternative definition for b because it's a lot easier to calculate. That's r times the standard deviation of y divided by the standard deviation of x. Okay. We didn't talk about what r is yet, but we did see how to calculate that in Excel. Okay. So that's the easiest way to go about it. So the reason that we get these values is because this is what minimizes the error, and that's what we want. We want the error to be as small as possible. Okay. So the book then makes a point of talking about the idea of the slope, which we already really talked about earlier. We can find that here. I think it was all the way back right here. The slope in general tells you the number of units y changes per 1 unit change in x. So putting this more into the variable language, it's the number of units that the dependent variable changes every time you change the independent variable by 1. Okay, so just replace y and x with dependent and independent variable. So it's just a little more general there. So in other words, it just tells you as you go to the right on your graph, what is y doing? Is it going up? Is it going down? And by how much? Okay. So the next thing we want to talk about is what exactly this r is. Okay. So this r, as we saw in the Excel that we were doing, is what's known as the correlation coefficient. Okay. So the correlation coefficient r. Correlation, in plain English, that's telling us what the relationship between two variables are, or if there is one at all, right? Are the variables correlated? Which essentially just means as one changes, does the other change? So that's going back to slope. And that's exactly what we're going to see is that the correlation coefficient, it tells us the slope of the regression line. It tells us exactly what the slope is, tells us how strong the relationship is. We can kind of see this if we go back and look. We see that b is the slope of the line, and r is a big part of what b is, right? So it's r times the standard deviation of each of these. Okay. So it's not exactly the slope by itself, but it's a big part of the slope. Okay. So the correlation coefficient R, it was developed by Carl Pearson. Pearson did a lot of work in statistics. You kind of hear his name a lot here. And here, let's write down the definition we have here. Correlation coefficient R is numerical and provides a measure of strength. Like I said, how strong the relationship is. And direction. So this is essentially, is your line going upwards or downwards? Okay. We would say they're either positively or negatively correlated, which we'll see in a minute. Of the linear association between X and Y. Okay. Or more generally, the independent variable and the dependent variable. So we always just use X and Y, but in practice, you would replace X and Y with whatever variables you're using. Like, for example, commonly instead of X, you'll use T for time. Okay. Maybe you have like temperature, something like that. Maybe you have like height. Okay. So it all depends. So how do we calculate this correlation coefficient first of all? So first let's look at the equation for it, and then we'll talk about how to interpret it. The equation, I'm just going to warn you right now, is it's a little messy, and it is definitely not something to memorize or anything like that because it's a big formula. Typically, you'll just want to do it in Excel, okay? Or you can use another program if you'd like to. But just to show you where it comes from, here is the formula. Okay. So R is equal to N. So N here is our sample size, just like before. N is the sample size. So N, and then the sum of X times Y's minus the sum of the X's times the sum of the Y's. So what this means is that you add all the X's together, you add all the Y's together, then you multiply whatever their sums are. Okay, so you do the addition first, then the multiplication. That's why we have the parentheses here. Let me write this a little better. Remember, these capital sigmas just mean to add them up. This is the other order. Here we multiply the X and Y's first and then add them together. Okay. So that's the numerator. The denominator, the whole thing is in a square root. And we're doing N, the sum of the X squared. So you would square the X's and then add them together. Minus the sum of X's squared. So the opposite again, you add the X's, and then you square them. Okay. And then the same thing with the Y's. Sum of the Y squareds minus the sum of the Y's. Let me see if I can move over here. Squared. Okay. So like I said, not a nice formula. Not something I would expect you to do by hand. You could do this by hand. There's nothing here you don't know how to do. It's just that it would be very tedious. So you would, especially if you have a lot of data. So luckily, we have things like Excel that just easily does it for you. Okay. So if we suspect that there is going to be a linear relationship between X and Y, then R can tell us exactly how strong that relationship is. Okay. So let's look at now what the value of R tells us. Okay. So first of all, the first bullet point here, the value of R is always between -1 and 1. Okay. So in other words here, -1 is less than or equal to R is less than or equal to 1. Okay. So the largest thing R can be is 1. The smallest thing it can be is -1. We saw that before. In the example problem we did in the last lecture, our R was 0.995. So it was almost 1. Okay. But it was within this range still. The size of the correlation R indicates the strength of the linear relationship between X and Y. Okay. So the size of it tells you the strength of the relationship, which we pretty much already established. So on that size, if R is equal to 0, there is likely no linear correlation, meaning relationship. Okay. And then it notes that it's important to still look at the scatter plot in this case because it's possible that data that has more of a curved relationship, so that is to say, it has a relationship. It's just that the relationship isn't necessarily linear. It might come out to have an R equals 0. So this is only telling you about the strength of a linear relationship. The fact that it doesn't have a linear relationship does not mean that it has no relationship. Okay, this is specifically about the strength of a linear relationship, which is important to note. Usually, if we get data, first thing we're going to do is test for a linear relationship because it's very easy to do, relatively anyway, compared to the other methods. If we find that there's no linear relationship, we don't automatically assume that there's no relationship. Now we have to start looking at other options. The scatter plot can give us a good idea of this. Okay, like here, for example, in this fourth one, we can see there's not really a linear relationship, but there is kind of a curved relationship, right? There's like a line going like this. Okay. If R is equal to 1, there is a perfect positive correlation. Okay. So this means that they're perfectly correlated and the relationship is positive, meaning your line is going to go upwards. It means that the slope is positive. Okay. If we remember, or if we look back, I guess, at B is our slope here, the standard deviation is always going to be positive no matter what. So whether the slope is positive or negative is completely dependent on R. So if R is positive, the slope's going to be positive. If R is negative, the slope's going to be negative. Okay. The slope being positive means you would have a line like this going upwards, whereas slope being negative, it would look more like this one where it's going downwards. Okay. If R is equal to -1, there is a perfect negative correlation. Okay. So in these cases, this would mean that all of our data would lie perfectly on a straight line. So like in the R equals 1 case, for example, that means that every single point of our data would be able to fit on a line. Okay. The one we looked at in the last lecture, where we had an R of 0.995, that means it was so close to every single point being able to go onto a line. There was just one that was a little bit off, that wouldn't fit perfectly with the rest of them. Okay. Now, in the real world, our data, of course, is not always going to fit on a straight line, right? But it could often be very close to being on a straight line. So we'll have maybe R values that are close to 1, but it's going to be almost impossible to find data where R is exactly 1. Okay. If we manufacture the data, like if we just make up numbers, then we can do it easily. But, just out in the wild, it's going to be impossible to find any data where the R is equal to 1 or the R is equal to -1, because these are both perfect relationships, and that's just not how data works. So, often our job is to determine, okay, what's the cutoff? Okay, so being at either extreme, 1 or -1, is perfect, and being in the middle at 0 means that there's no relationship. So what if we're at like 0.5, and there's like half of a relationship? What does that mean, right? So we need like a cutoff point. So let's, before we do that though, I'm not going to write this down, what it says next, because we've already talked about it a few times, but just to reiterate, when the sign of R is positive, if R is positive, that means that the slope of the line is positive, which means that your line's going to be going upwards. Okay. So this means that as X is increasing, your Y is also increasing. Okay. By how much, we don't know. But if R is positive, as X increases, Y increases. Okay. So maybe I'll write that part down. R positive implies as X increases, here, let me write it. As X increases, Y increases. Okay. So as you go over horizontally, you're also going up vertically. If R is negative, it's going to be the opposite. Okay, R negative implies as X increases, Y decreases. Okay. So as your X goes this way, your Y goes this way. Okay. So as we go over to the right, Y is getting smaller. So one thing we should note is that just because even if things are perfectly correlated, it doesn't necessarily mean that there is causation. We often, we as in the general public, when we're looking at statistics, we often confuse the words correlation and causation. And articles often will look at statistical studies where they establish correlation and get it mixed up and report that there's causation. We see this all the time with things, for example, like you'll see some articles claiming that exercise can cure depression. Okay. Whereas it's really, what we see is that there is a correlation between exercising more and being less depressed. The thing is, we can't establish causation there. We could say, okay, if you exercise more, if you exercise more, it alleviates your depression. Or it could be the case that if you're less depressed, you're more likely to exercise. Or it could be some third outside factor that's affecting both of them. Okay. This was pretty popular. There were some studies claiming that diet soda caused obesity, because that there was a correlation between drinking diet soda and obesity. But it was just that, it's a correlation. There was no clear indicator that drinking diet soda would cause obesity. In fact, it's completely counterintuitive because obesity is typically caused by excess calories, which diet soda doesn't have. So it could have been the case that drinking diet soda caused obesity. It could be the case that the more likely logical case is that if somebody is struggling with obesity and is trying to lose weight, they're more likely to drink diet soda, right? That's the market that diet soda is appealing to, is people trying to lose weight. So there's a lot of overlap between people with obesity and people drinking diet soda. So that's why there's a correlation there. It's not that one is causing the other, it's that that's what the market is, right? Whereas if people that are at a normal weight, they're not typically drinking diet soda, right? They're not like looking at calories as much. They're just, drinking the regular soda, not really thinking about it. So they're less likely to drink diet soda. So there's a correlation between drinking diet soda and obesity, but it's not the case at all that you can jump to diet soda causing obesity. Okay. But a lot of articles, when those studies were coming out, a lot of articles did do that. And it was just, it was completely false. And that idea still is kind of pervasive in our mindsets now, just because there was so much false reporting on that a long time ago. We still kind of think of diet soda as dangerous. Whereas there's never been any real conclusive evidence that it is anywhere near as dangerous as regular soda. Okay. So, for calculating R, we already showed how to do that in Excel, and we'll do some more examples with that too. When we're interpreting R, though, it's more common that we actually look at what's called R squared. Okay, so let's look at that. So this R squared, it's known as the coefficient of determination. Here, actually, let me write it like this. The coefficient of determination, R squared, is the square of the correlation coefficient. Okay. Remember, so this just means R times R multiplied by itself. It is usually stated as a percent. Okay. Let's think about that. R is always between -1 and 1, right? If we then square R, that means that R squared is always going to be between 0 and 1. Okay, if R is 0, R squared would be 0. If R is 1, R squared would be 1. If R is -1, R squared would still be 1. Because any negative times a negative gives you a positive. And when you multiply numbers between 0 and 1 to get it by itself, they stay between 0 and 1. You can think about like doing 1/2 times 1/2, you get 1/4, right? It's still between 0 and 1. So it's going to be a number between 0 and 1, so it makes sense that you can represent it as a percent. It'll be between 0 and 100%. The reason for this is that R squared represents the percent a variation in X, no, sorry, in Y that can be explained by variation in X using the regression line. Okay. So it's essentially saying how much of Y can we explain via this relationship with X. Okay. And it's giving us a numerical interpretation of that. So the book doesn't say this right here anyway, but a good rule of thumb is that if R squared is above 0.7, it typically means they have a strong relationship, so above 70%. And if it's above 0.5, we typically call that a weak relationship. So above 0.5, we say there's a weak correlation. Above 0.7, we say there's a strong correlation. And below 0.5, we just typically ignore that. We say that there's not really a good relationship there. Okay. So on the other hand, 1 minus R squared would represent the rest of it, the amount of Y that's not explained by X. Okay. Okay. So if we just think about, for example, that I didn't save a copy of it, the data we were using last time. Let me see if do we still have it? Yeah, we're using this data. Okay. So we did 2000, 2002, and we only need the correlation coefficient this time. We don't need the rest of it. Okay. So our R, we go to formulas. And let me make this a little larger here. There we go. All right. So R, we go to formulas, statistical, and it was the choral. And then we take our first array. It doesn't actually matter which one is which. Okay. And we get our R. It actually is rounding to 1, which we don't want because we know it's not a perfect relationship. So if it doesn't have enough room to display the decimals, it'll just round it. Okay. So let's make this bigger. So we see R is 0.99565. So R squared, we can just make a formula for that. We're just going to take A7 and you can just multiply it by itself. So times A7 is, it's saying 1 again. It's not going to be actually 1 though. 0.9913. Okay. So if R is really large, R squared is going to be really large. So we would say that these are very strongly correlated. Okay. If we change some of this, like maybe we make this a 10, it's going to change everything. Okay. So now they still would be strongly correlated, but not quite as strong. Change that to a 1. Now it's going down even more. Say 2004 was way off of everything else, like maybe it was 100. Now it's going to be just barely strongly correlated. Okay, so it still is though. If we make this 0 and this 0 and this 0 and now this is 100, now the data is not very correlated at all. Okay, there's a less than a weak relationship between them. So this is at the point where we really wouldn't even be looking for a linear relationship at all anymore. Okay. Okay. So that is the end of 12.3. So let's go back. Let's go into 12.4 now. This is where we're actually going to test um, whether there's a good correlation or not. Okay. Okay. Actually, 12.4. It just goes through. Okay, how do we determine if the regression coefficient is significant? Um, and it does it by using a hypothesis test. So that would be the proper way to do it. The zero 0.5 and 0.7 rules I was talking about, that's more of just a general rule of thumb. But for our cases, it'll be good enough. So we're not going to go through 12.4. What I'd like to do instead is now go through another example. Okay. So this is from the practice section of chapter 12 here. We're going to use this data. Let me go ahead and get rid of this data. Whoops. Okay, so we'll delete that. Here, let me, I'm gonna need to shrink the size back down while I put the data in, and then I'll increase it again. So, first let's look at, let's look at this table right here. So what are we looking for a correlation between? Well, at first glance, you might think it's the last two columns, but that would not be the case. These are both dependent variables. Instead, our independent variable is the year. So we're going to look to see if there's a correlation between the year and the number of flu cases diagnosed. And then we can do a separate test to see if there's a correlation between the year and the number of flu deaths. Okay. So we'll just take all of the data first. It's a little difficult to highlight. You can leave out the totals here. Don't really need that. Okay, so we'll put that in. I don't think that worked right. So you want to maybe do, match destination formatting. It's going to be the best way to do it. Let me increase the size here a bit. I want to make sure it's all on one page. Okay. So hopefully that's big enough. So one thing I did was, if you're going to be using Excel a lot for correlation, it's helpful to add in this thing called a data analysis tool. And the way you do that is you go to File, you go to Options, you go to your add-ins, you go to Excel add-ins, you want to manage those. And the one you're looking for is the Analysis Tool Pack. So this is built into Excel. It's just not available by default. So you just want to click that, then press OK. Unfortunately for Google Sheets, I'm not really sure if there is a tool like this. I'd be surprised if there wasn't, but I'll show you how to do it with the formulas either way. We're really just looking for the R and R squared here, so you can do that pretty easily with the formulas. Now, one thing that you might notice right away is that this is going to be a problem, right? Because this isn't exactly a number. This is just pre-1981. So what should we do with this? Well, one thing we can do is just ignore it, right? We could just say, we can just look for a relationship between all of the other ones. That's probably the best way to do it. You can't exactly change it to 1980 because then it's not accurate, right? This isn't just 1980, it's all the years before 1981. Okay. So we'll just probably just ignore this first column or this first row and just look at 1981 onwards. Okay. So let's take a look at what this data analysis tool does. And when you click on it, you'll see there's a lot of different things you can do with it. You can find the correlation, covariance. What we're going to do is we're going to look at the regression, okay? Because that's ultimately what we're doing is we're trying to find the regression line. So let's do that. We want to put our y range in. Remember, your y is your dependent variable, which is going to be this. And then we want to put our x is in there. And then notice you can set the confidence level. So we can set it to 95%. That's what it'll default to, so you can just not worry about that. All of these you don't really need too much. You can set some labels if you want to. It's not really too important. You can set this so that you can have the, you can actually graph the regression line. That's what the line fit plots will be. So let's just go ahead and do all that. And this is what it comes up with. So let me make this bigger. There we go. So what you might notice, first of all, it made a new sheet. You can see at the bottom here, my data's on sheet 1. So it made this, it made it on a new sheet because it gives us a whole bunch of stuff. A lot of this stuff we've never talked about, so don't worry about it too much. But let's talk about the stuff that we do know about. It kind of squishes it all together, so you want to make these a little bigger. Okay. So first of all, let's look at the graph, right? You can see it plots the data as a scatter plot. First of all, the blue points are our data points, and then the orange line is the regression line. So it's saying, okay, this is what our data looks like. Here's the best fit line. Is that a good line? Well, really, it doesn't even look like there's a very good linear relationship between them, right? It looks more like a quadratic function, if you remember that, if you took college algebra. But either way, it actually kind of looks like the normal distribution almost. It's just kind of lopsided. It doesn't go all the way back down. So it definitely doesn't look like there's a linear relationship. And if we look at our r squared, which is right here, you can see that, right? I said 0.5 and above means there's a weak relationship. This is 0.2. So there's almost no relationship here at all. So that's not something, so this shouldn't be too surprising here. So let's, this gives you your sample size, okay? Multiple R, that's not something we talked about, but in this case, because this is like your R value for if you have multiple variables, we only have one variable here. So this is just like our regular R value. So you can see the relationship is positive, as we see on the graph here, but it's still not a very strong relationship. Adjusted R squared is just another type of R squared, which we never talked about, so don't worry about that. ANOVA is what we're going to do in chapter 14 or 13, and same with the F statistics and stuff like that. You can see some familiar words here, right? Like your T statistics, your P values, your lower 95%, your upper 95%, meaning the tail parts of that, the bell graph. Okay. This is telling you, okay, this is your, for your data points, this is telling you what, based on the line, what they're predicted to be. And then the residuals is telling you how far away the actual data point is. So that's back what we did in 12.1 with the whole absolute value thing, except it's not taking the absolute value because you have some negative numbers. This is telling you how far away your data points are from their predicted data points. Okay, so you can see some of them are pretty far away. And this all goes back to the fact that this really doesn't have a linear relationship. Okay. So this gives us lots of information, more than we know what to do with right now. If you just wanted the R value, again, you would just go to your more functions, correlation, and then you take your one column, and put it in array 1, your next column in array 2, and then you get your 0.45, which is the multiple r right here. And then you can square it for your r squared. Okay. If you wanted to actually find the regression line, notice it doesn't actually give it to us here, right? I think most of the information is in here. You just kind of have to dig it out. It plotted it for us, so it's not really important to actually have the formula. So yeah, I think we would just have to do that by hand if we actually wanted to get it. I think it might be buried in here somewhere. I'm just not sure. You would actually want the equation if you were going to use it to predict later cases. Like, so for example, if, you know, in our data, this goes up to 2002. If we wanted to predict what's going to happen in 2003, we would need the line. But we're not going to do that with this line anyway because it doesn't have a good relationship. Okay. So let's look at the flu deaths with the year and see if there's a better relationship there. Okay, so we'll go back to our data analysis tool, and we're going to do regression again. Okay, so this time, instead of that one, we're going to replace it with this. Okay, and I think this should all be fine here. Let's see what this does. This might give us the actual what's it called? The actual formula for the line. Let me see. I don't see it anywhere. No, I think you still have to put it together manually. Okay. Well, anyway, whoops. But it gives us this nice graph. Again, it's kind of squishing everything together. But you can see, again, this looks pretty similar. Like, there's not a very good linear relationship here. And if you go back to this, you know, you can see with your r values here and your r squared that there's not a very good linear relationship here. Okay, so this is basically just the same as the last one. You know, let's go ahead and look at our other data where there was a good linear relationship, just so we can run this test on it and see what happens. Oops, where was that? 12.2. So we have 0.5. Sorry, that's backwards. 2000 to 2002, 2003, 2004, right? 0.5, 20, 33, 47. Okay. Just so we can see an example of one where it does work out pretty well. Our Y's are these numbers. Our X's are these numbers. Let's go ahead and do that. It's always going to make a new sheet for this. Okay. Whoops. So this is kind of interesting, the way it made the line. It didn't actually connect the line. It didn't on the other ones either, but it kind of gave you more of a shape there. I don't know if there's any way to actually connect them or not. I don't see a way to do that. Like on these ones, it didn't connect the dots either, but you can see more clearly what the shape of the line was because there were more data points. This one, there was only 4 data points, so it's hard to make out exactly what the line looks like. But anyway, you can see your r squared is 0.991, your r is 0.995, so there's a good linear relationship here. They're almost all of them are very close. The predicted values are very close to the actual data values, and that's what we're really measuring here. Okay. I think right here, actually, yeah, this, now that I'm looking at it, this is giving you the formula for the line. This is your B and this is your A. That's what we calculated last time, right? Our A is the negative 22,057 and our B was the 11.52. Okay, so I'm glad we looked at this so I can see that now. So that means for the regression line on this one, your B would be the 1749 and your A is this negative 3 million. Okay. And this one, your B is 1109 and your A is negative 2 million or so. Okay. So those are the values you'd be using if you're trying to predict later numbers. Okay. This one, it would be a good idea to do that using this line because there's such a good relationship. These ones, there's not a good relationship, so we wouldn't do that. Some of you actually, let me see if I have it. Some of you had that survey data in your previous sociology class, Sociology of Education. You helped me make this survey data. Let me see if I have it saved. Yeah, I went through and I ran that data analysis for all of these questions, and I looked at the correlation. And you can see I found, I made a little chart here for, I don't know why I did absolute value of R. I should have done R squared, but it's not really that important. You can see I found almost no correlation with all of them. All of them had a very low R squared value. Let me see if I can. I think I did them on another one, and there was just too much information, and I was sending this on to my boss, the provost. So, sorry, I was sending this on to Dr. C. So I just summarized it all here. I don't think I actually kept the data analysis for it, but yeah, you can see this was how I got these. I found what the R values were for all of them using that data analysis tool, and then I made the summary right here. So there was almost no correlation between any of the variables, which meant that those surveys, we didn't really end up being able to do much with them, okay, because there was no significant data from them, okay. All right, so I think that pretty much wraps up chapter 12. So, next time we'll start looking at chapter 13. We'll do what we can from there with the time that we have. And yeah, thank you for watching today, and I will see you then.